Excellent. No worries. Thanks so much for having me today. So as mentioned, my name's Emerson Keenan. I'm here from Australia, from the University of Melbourne, where I'm an honorary research fellow in the Department of Obstetrics, Gynecology and Newborn Health. I'm also the CEO and CTO at Carly Healthcare, so I have a conflict of interest that we do have a technology in this space. And today I really want to talk about, I think we've touched on a lot of this throughout the presentations today, kind of the drivers for fetal monitoring and identifying fetal complications early and balancing outcome measures. So, if we're monitoring during pregnancy, we're trying to balance between early intervention, but also picking up, conditions of interest, making sure we don't have these adverse outcomes. And so throughout pregnancy, we're doing repeated monitoring when some risk factor is present. And so really our belief is that, having better monitoring technology that can pick up these conditions earlier and more accurately can both prevent unnecessary hospitalisation and intervention, but also improve maternal and neonatal outcomes. So as part of this vision for fetal monitoring, I see the technology as kind of having three components. So firstly, we want technology that can monitor over extended durations. So something that can potentially monitor those raw maternal and fetal physiological signals over a period of days to weeks. Next, it should be able to extract maternal and fetal parameters from those signals. So we need algorithms that can pull out things like the maternal heart rate, fetal heart rate, uterine contractions throughout daily activities. And finally, what will be the focus of what we're looking at today is the ability of edge AI models that can operate without internet connectivity to interpret these signals and make clinical risk predictions on the data that's coming through. And so the model we're really thinking about here is what we call the Apple Watch pregnancy, so the Apple Watch model for pregnancy. And so, just as an example here, some of you may have heard, the Apple Watch has a feature to detect atrial fibrillation. So there's been many studies showing that it can actually better pick up atrial fibrillation than the standard of care. So the idea is that this kind of model of more continuous monitoring and picking this stuff during daily activities can help us better identify these cases where fetal injury is occurring. Now, it is a very complex problem, and so I want to lay out what are the key things we need to solve to make this a reality, and then dive a bit more detail into the age AI models themselves. So firstly, we need to be able to acquire these signals in a friendly way over extended time durations, and so for this we need things like wearable ECG monitors, might be acoustic monitors. I know Antonio's speaking soon about wearable ultrasound, getting reliable signals in a comfortable and usable way. Next, we need to extract the parameters from these things. We need to be able to get that fetal heart rate, maternal heart rate, and uterine contractions. And so I know Nicola talked about this, the signal quality and being able to really get this in all these different conditions is a really hard thing to do. And the ability to handle artifacts and do real-time signal processing is difficult. Once we have that, we need some method of AI to take in all these signals, come up with some interpretation, and actually implement that on the device in a way that we can make these predictions in real time. And so to do that, we need large CTG data sets, we need good outcome measures, we need the ability to cross-validate these outcomes, looking at data across countries and different institutions, and then really being able to do this in real time. Following on to this, it doesn't end at the technology. We need the ability to then triage these conditions to know when, at what risk level do we actually need to make an intervention, and when can we safely let someone stay at home and that pregnancy continue. And so to do this, really need to work with clinicians and lots of stakeholders to understand the best way to do things like alert design, those clinical decision support tools, what is acceptable to users, and integrating into workflows. And finally, there's also the regulatory and commercial piece. We need to understand what is the correct indication for use, what patient population do we use this in, what are the reimbursements behind this, how do we deliver the care, and finally, what are the health economics? Where does it make sense to actually use this model in practice? So there's a lot of questions here, but I really want to focus on one today, which is the thing we've been looking at recently, is the ability to run these AI models locally on devices and kind of decoupling the need for internet connectivity. So cardiac analysis takes in at its base layer those fetal signals I was talking about, and you might acquire them from various number of devices. And kind of in practice, we see really the fetal heart rate's typically acquired using a Doppler ultrasound, or either in labour you might get a direct fetal ECG, or more recently the non-invasive fetal ECG. And then for uterine contractions, you'll get that from an external tocodynamometer, an intrauterine pressure catheter, or also the non-invasive electrohistogram. So in clinical practice, either it's interpreted manually by a clinician, or there's been work done over many years to develop computerized methods that take in CTG data sets, perform some pre-processing, and then classify it according to some criteria. There's been different ways of doing this, everything from logic methods that mimic clinical guidelines to feature-based machine learning, or even more recently, deep learning. And so, we're trying to classify these in different scenarios, and so, some scenario metrics might be classifying into either a normal, suspect, or compromised, or we might even have a binary classification, which is just a reassuring or non-reassuring CTG trace. And we published a paper last year in IEEE Journal of Engineering and Health Translation. So we did some work just around interpretability of these methods. So this is a deep learning method we developed, which is looking at predicting low fetal pH. And so the yellow sections you see here is where the model is predicting the likelihood of that fetal hypoxia state. And so what happens is you'll take this, input recording, generate these candidate predictions, and really at the end of it, we get some probability at the end that says, either the model is confident that there is some fetal hypoxia present, or it's not confident. And so you can think about this as a risk stratification. Now, most of these methods for deep learning have typically been implemented on graphical processing units. And so a review we conducted a few years ago found that the state of the art has been achieved using deep learning methods, particularly for this predicting of low fetal pH. And this is practical for a hospital-based system or a system that has internet connectivity where you don't have power constraints. But if we're looking to do this where there is no internet, where we can do this continuously, we need something that can work in a much more low power form factor. And so what we're looking about is the ability to do long-term monitoring on a wearable device. And so we need something that can run for more than 24 hours on a very small battery, something without internet connectivity being always available, and also ideally no degradation in performance. We want something that can accurately predict these scenarios just as good as our GPU-based methods. And so for this study, we used an internal data set that we collected at the Mercy Hospital for Women in Melbourne, which has almost 10,000 labouring fetal heart recordings from a larger database, which was collected over a period of about 10 years. There's only around a 1% rate of those low fetal pH in that data set, as well as using the CTU UHB data set, which is a public data set of around 500 recordings. And so for our classification task, we used the last 60 minutes of fetal heart rate data, with the true classes being pH less than 7.05, and anything above that was considered not compromised. Now, I want to be really clear here. I understand this is a very strong limitation that we're using intrapartum data to kind of prove out this scenario, but it's very difficult to get labels in antepartum settings to understand really where that fetal compromise is occurring. So we do want to look at that in the long term. For now, this is a bit of a proof of concept using the data set that we do have. The experimental setup was that we're using a what's called a ResNet model. So essentially we start with a full precision model, which is something that's implemented on a computer, and we look at compressing that down onto something that can run on a wearable device. And so to do this, we used a new chip that's been released recently called the MAX 78002, and we had a small evaluation board set up where we could measure the power consumption of that chip, as well as the inference, so the predictions of this device. And so that chip is about 12 millimeters by 12 millimeters. It's a very small device that can be used potentially in a wearable device. And we essentially sent the fetal heart rate data into this board and then measured out our classification result. The way we did our training, so we took our Mercy data set, which was around 10,000 recordings, split that into 80% training data and a 20% validation data set, which we used to refine the model, and then did external testing on that CTU UHB data set. So one thing I want to highlight is that these chips have really, really tight limitations. They can only store about 1 megabyte of data. The model weights are limited to 2 megabytes, which means that in order to actually make this feasible, we only were able to use that 60 minutes data at a 0.5 hertz sampling rate. And for knowledge, clinically we usually work at a 4 hertz sampling rate, so we're only having data points once every 2 seconds. So we are kind of limited in how much data we can put into it. We looked at this ResNet model, which was adapted to that chip's constraints, and we tried 3 different training strategies. So we looked at what's called post-training quantization, which is to train the model and then kind of compress it down to the chip as the final step. Something called quantization-aware training, where we actually factor in throughout the training process the need that it needs to go to the chip at the very end. And then finally, something called knowledge distillation. And I'll talk a bit more about that in more detail later. This is a very engineering-heavy point, but it was something really interesting for us in the process of developing the implementation, was that most of these prediction models use something called a softmax, or a classification layer, at the very end of the process. And so we found when we first started designing it, the quantization, which is the limiting factor at the very end, made the predictions very poor in its default scenario. So we had to actually scale the inputs at that softmax layer to actually get a good prediction. And so what this meant is that we were, before passing it to a classification, we were multiplying those values to get a better range of outputs. So you'll see kind of this stepped graph here, but this multiplication kind of spreads out the prediction over the whole model range. And we found that by doing a 4 times multiplication, we achieved kind of the optimal scenario, which is that picture shown in the middle there. And this was used throughout the rest of our training process. We measured the inference energy and time taken. So this is how much power is consumed by every time we want to do a prediction on the device. And probably as expected, we found that the inference energy and the time to inference increased with the sampling rate, so the more data we're putting in, as well as the larger model weights. But overall, all of this was very achievable. And so even at the highest setting, so using an 8-bit quantization with a 0.5 hertz sampling rate, we could achieve 1 million inferences on a 500 milliamp battery. So we can do many inferences on a very small phone battery. In terms of the outcome performance, we found that the best performance was achieved, again, using that highest range setting, the 8-bit weights and the 0.5 hertz data. Interestingly, we did find comparable test performance for the 0.25 hertz data, which maybe says something that, across different data sets, there are different characteristics of the data that's involved. You might get different performance, so that was an interesting finding for us. But overall, using that highest level of data gave us the best results. One of the really interesting things that we found was this knowledge distillation process. So what knowledge distillation is that we take our original model, so the one that was trained on the graphics processing unit, and then when we're training that smaller model, we let the big model kind of guide the smaller model during training. So what this means is that generally when we're doing machine learning training, we're training against something called a loss function, which is telling the model when it's correct and when it's not. And so rather than just using those outcome labels, so showing it a piece of data that says, hey, this was hypoxic or not hypoxic, we show it that, but we also say, and hey, here's what the teacher thinks. So really interestingly, so having that secondary model, so the teacher model saying, hey, here's a case, this is what I think about it, as well as the true label, increased our model performance quite significantly. And I think this says something really interesting in the case of CTG classification, in that sometimes your labels aren't very good. You might have something that you think is hypoxic that actually wasn't at the time you had your CTG data, or vice versa, you have CTG data that's showing some decelerative pattern, but intervention occurred, and then the final label was actually showing the baby was good because the intervention successfully rescued that baby. So I think this is really interesting, this finding that potentially having someone to kind of say, hey, this baby says it was hypoxic, but I know for another reason that it's not really, was really interesting for us. And so the final performance comparison we found is that full precision model achieved an AUC of 0.81. The post-training quantization was the worst with the AUC of 0.74. The QAT was AUC of 0.77, but using both the knowledge distillation and QAT, we're able to get the same performance, so that same 0.81 AUC using this much smaller model. And now, just to give you an idea of the kind of clinical performance, so evaluating on that test data set, the true positive rate at 6% false positive rate was around 35%, at 13% false positive rate about 43%, and at 24% false positive rate was around 75%. So this is matching kind of what's been achieved in the literature. I think there's still room for improvement, but it's promising to see that we can do this on a very small device with similar accuracy to a full GPU implementation. So as I mentioned, we've got that equivalent AEC performance. It's a 95.4% saving in energy compared to the baseline, and a much smaller model. So the final model was only around 73 kilobytes, which is interesting that we can compress all of this knowledge into something that's smaller than probably the Word documents on your computer. And we've got a full hardware implementation available, so on that GitHub link there, if anyone's interested, you can see how it's all been created. Now, the key takeaways, I think, are that firstly, this real-time fetal compromise detection is possible on low-power edge AI chips. That 8-bit quantized model with a 0.5 hertz sampling rate achieved the best performance. With a typical 500 milliamp hour battery, we can do 1 million predictions. And just for your knowledge, an average smartphone is around 3,000 to 4,000 milliamp hours. So we're talking much smaller than a smartphone battery. For next steps, we want to look at developing an integrated wearable device that combines all these pieces together, the ability to acquire the signals, to extract those maternal fetal parameters, and do the AI analysis all on one device. And also incorporating other maternal fetal clinical parameters and looking at other prediction scenarios. As I mentioned, looking at these longitudinal prediction or antepartum prediction scenarios. So I think, going back to that visionary, set of tasks, we're making some progress, I think, on the technical elements. There is, the building blocks of all these pieces to make something technically that can achieve this. But I think the really interesting part is these last points around triage and clinical impact, and we really need cross-disciplinary work to understand how to advance these domains. So, if there's something interests you, I'd love to talk to anyone in the room about how we take this to the next step of implementation. I just want to say some quick thank yous to our team. So firstly, the Kali Healthcare team and the first author of many of these papers, Lachana Mendes, done absolutely amazing work putting this together, as well as our research collaborators and funders. And thank you so much for having me here today. There's a link to the full paper on screen here, and happy to take any questions.
So thank you very much. This was really very impressive, I have to say. But let me first check if there are questions.
Hi, it was really nice work. I really enjoyed your presentation. When you said about sampling at a lower sampling rate, I was wondering if you considered non-uniform sampling, and yeah, that's my question.
Yeah, that's a very good point. We actually didn't look into that, so that's probably something we should look at, is maybe looking at chunks at longer durations.
Yeah,
that's a very good point, yeah.
And maybe then it doesn't have to be fixed sampling, low sampling rate, but that depending on when you need more information, that you can do more sampling, but then the rest, yeah,
it's a great idea. I think we'll look into that. Thank you.
Thanks, Emerson, for your talk. Very interesting. Often, in the spectrum of things, where does the computational go? Where should the engine live? Should it? We just say it can go wherever there's the computing power, and keep the acquisition very light. You have gone full in on edge, and I think it's interesting. You've spent time on the modeling side at full precision, but you've also made a huge commitment to making it local hardware with a local. I think this has interesting implications for the rest of us who maybe have only time to do the full precision modeling, and it's a proof of concept that transition or that transfer is possible. I don't know if your insights can somehow be shared with other researchers.
Yeah, so do you mean the insights in terms of how we compress the models, or? Yeah. Yeah, so I think there's a lot that goes into it. I think I touched on a few of them, some of the things just around understanding the effects of quantization, and that, for example, that softmax trick we worked out did make a big difference, as well as that knowledge distillation piece. I think, some of the things I'm thinking about is just the practicalities of the use case. Internet connectivity can be a big issue. If you don't have reliable internet connectivity, you're trying to do this diagnosis and monitoring in a remote setting introduces a big challenge. So pushing it all to the edge just removes that huge barrier. Also if you can do this on the device, you don't need a Bluetooth connection. You can be doing this all locally on the device. There might be just some simple, light display that kind of indicates, hey, there's something that needs to happen. And you remove all those kind of barriers to things going wrong by kind of pushing it right into the edge device. But I think that there's a lot of work to be done in the full precision space to understand, what outcomes we're trying to predict, understanding the risk factors that works. But this is that proof of concept that, if we can work all that out, it is possible to do this all local on a device.
Okay, so then thank you very much again. And then